Okay, so we will look at oblique collisions of particles. To begin with today. So for example, suppose we have a situation like this. We have two bodies or two particles which are moving with initial velocities, which are like this, let's say. So along this kind of path and this kind of path. And eventually after some time, they collide. So as they come in contact, suppose this is the center to center line, they will experience impulses like this. Collision impulse on 1 due to 2 and collision impulse on 2 due to 1. So these two will be equal and opposite of each other. And as a result of these collision impulses, eventually after the collision is done, that is, after they have finished being in contact, they might move off with velocities which are like this. So the equations available to us here are momentum conservation, but that becomes a vector equation. And the coefficient of restitution equation so these equations are used for solving. Okay, so given u1 and u2 as two vectors, and of course m1, m2 and coefficient of restitution, we can find out the unknown vectors v1 and v2 using this general procedure. So let's understand with examples. Now, obviously, the solving is a little bit more difficult compared to the 1D collisions we have seen before, because now it involves two-dimensional vectors or vectors in a plane rather than one-dimensional conservation of momentum equation along one axis. And usually the problem is such that there is some extra information given indirectly through the question, so that the solving becomes feasible or the solving becomes workable. So let's understand how that works out. Especially the coefficient of restitution equation, the approach and separation velocity. To be able to calculate the approach and separation velocities, some information has to be known about the angle at which the contact is happening, or basically the angle made by the initial velocities u1 and u2 with respect to that line of action of the collision. Okay, the line along which the collision impulse J is acting, the center to center line. So typically the question gives us some information about those type of angles, etc. That's how these questions are worked out.
So the tangential component is conserved, right?
Yes, the tangential component of momentum gets conserved individually for the particles, and the component of momentum along the center to center line, or rather you can say even the component of velocities along the center to center lines, that helps us understand the approach or separation velocity. Just a moment, I'll reshare that file. Okay, so let's understand with an example how this works out. Okay, so the easiest level of question is such that just momentum conservation needs to be applied, because the rest of the things are quite simple. So suppose we have this kind of a situation, that this particle of mass m1 is moving with some velocity v naught like this initially. And it hits a stationary but larger particle or larger body here of mass m2. Okay, now it is given that okay, now after impact, m1 is deflected by 90 degrees, okay, and m2's velocity is at 53 degrees with respect to the line of the velocity v naught. So if v naught is equal to 5 meters per second and m1 loses 60% of its kinetic energy, So you want to find their final velocities. So as you can see in this question, a lot of information is given to you. Okay, so the question then just involves solving of simple momentum conservation, but in 2 dimensions. Okay, and here there is nothing to do with coefficient of restitution and separation and approach velocity. So this is the simplest level of question, okay, that you can get for oblique collision, because it does not involve anything to do with coefficient of restitution, and a lot of information is given to us. Let's understand what all information is given. So you can see that what is given is that V1, that is M1's final velocity, is at 90 degrees with respect to V0. That is the first information that is given, because it says it is deflected by 90 degrees. Okay. And it is also given that V1 will be equal to, now see what is happening. M1 is losing 60% of its initial kinetic energy. Okay. So that means, and V0 is 5 meters per second. So half M1 V1 square will be equal to 40%. So that is 0.4 of half M2 V2 square. So V1 square is 0.4 times V0 square. So V1 is this. Okay. So you can say that V1 square is 0.4 times V0 square. That's another information which is given through this. Okay. And of course, V0 is equal to 5 meters per second. Okay. So ultimately now we just have to find V2.
So I think it should be 0.6 into half M2 V2.
It loses 60%. No? So the remaining is 40%. You understood, no?
Ah,
Okay, so in fact, there is some extra information given in the question. This much information is not required. Actually, let's modify the question. So suppose this information is in fact not given to us. So let's say this information is not given. Only V0's value is given. So let's see in this case what happens. Okay, now what is given that this is at 53 degrees with respect to the line of. So let's see what this information tells us. Okay, so V2 is at 53 degrees with respect to V0. So let's see what this basically means now in terms of geometry. So this means that after impact, if this particle goes off with a velocity v1 like this, which is perpendicular to this line, then this has to go off with v2 like this, such that this line is at an angle of 53 degrees with respect to this. This is what this means. So this will be enough to solve actually the problem. Therefore, I said that extra information was given which you don't require. So now you can see that if we just apply momentum conservation between, because the masses are known, okay, so we apply momentum conservation between this diagram and then this diagram. So that is going to be sufficient because we know the masses. Masses are 1 and 3 kg. So momentum conservation here will be m1 into v0. This one was at rest, is equal to m1 v1 plus m2 v2. So now we can convert this into component equation by taking this direction as our x-axis, this direction as our y-axis. So when we write the x component of this, we'll see that we'll get m1 v0 is equal to m2 v2 cos 53. Okay. And when we take the y component of this, the initial y component of momentum is 0. And finally, it is plus m1 v1 minus m2 v2 sine 53. So we have two unknowns v1 and v2 we can calculate from this. Okay, so just substitute the values and work this out. Yes, very good, Anirudh. That's correct. Okay, so let's verify the answer. Yes, Kirti, that's correct. So V1 should be 6.67 or 20 by 3 meters per second, and V2 will be 25 by 9 or 2.8 nearly. So equation 1, we substitute M1 and M2's values, become V0, which is 5, is equal to 9 by 5 V2. So from this we can directly get V2 as round off to first place. And from equation 2, so these are the speeds. So this is the simplest type of question that you can get. Okay, so let's move on to different type of question now. Now suppose in the same example or something similar, one less piece of information is given. Okay, but instead coefficient of restitution is given to us. Suppose we have that kind of situation. So we have M1 equal to 2 kg, suppose, moving at 10 meters per second. This again comes and hits a heavier particle or heavier object M2 at rest initially. Now suppose again it is given that M1 deflects by, this time let us say, 60 degrees, okay, and M2 moves at 60. So this time instead of M2's direction, what is given to us? If the coefficient of restitution okay. So now you can see that this is slightly more complicated question in comparison. Okay. So here, what's going to happen is that as M1 and M2 come in contact, see that's the center to center line. So collision impulse acts along that line. And after impact, you can see that it's given to us that this velocity V1 and this velocity V2 be such that this is at 90 degrees, but this is some unknown angle. Let's say this is theta. So once again, comparing the momentum conservation equation, okay, so we can see that M1 V0 is M1 V1 plus M2 V2. So this gives us two equations now. So we have these two unknown equations, in which V1, V2 also unknown and theta is also unknown. So we need a third equation. And that is where the coefficient of restitution equation will come in. So first let's write down these two equations. So 20 is equal to 5V2 cos theta and 2V1 is equal to 5v2 sine theta. That's our second equation. Okay. Now let us understand the concept of approach and separation velocity in this. So just before impact, this is what the situation looks like. This has a velocity v naught, which is like this. So along the center to center line, v naught has a component of cos theta. So the approach velocity is how much? It is v naught cos theta. Okay, let's work it out. And just after impact, you can see this is our center to center line. Then this velocity v2 is along that center to center line because the impulse acts along that line. Okay. Whereas this body's velocity v1 such that it is, this angle is 90. You can see that this angle here, this will become 90 minus theta because this angle here is theta. So the separation velocity here will become how much? It will become v1 cos 90 minus theta, that is v1 sine theta plus v2. So the separation velocity is v1 sine theta plus v2. Okay. So now let us use this equation for coefficient of restitution, which is given. So it means that this separation velocity is equal to E times the approach velocity. So the separation velocity from here is how much? It is v1 plus v2, sorry, v1 sine theta plus v2. That is 0.6 times v naught cos theta. So we have v1 sine theta plus v2 is 6 cos theta. So that is our third equation. Okay, so from this we will have to find out the three unknown quantities. Okay.
So,
Yes.
so can you explain how that V approaches V naught cos theta?
Yeah, we approach is, see, the particle m1's component of velocity directly towards the center of v2 is how much?
Oh, okay, V naught cos theta. Yeah.
Yeah.
Okay.
Similarly for the separation velocity,
Yeah.
is the relative velocities components along the center to center line.
Sir, I send the answer.
Yeah. Yeah, we'll verify that. Okay. Right. So let us see the solving of these equations. So we have 5v2 cos theta is 20 and 5v2 sin theta is 2v1, or v2 cos theta is 4 and v2 sin theta is 0.4 v1. Okay. And then we have this equation that v1 sin theta plus v2 is equal to 6 cos theta. Okay. So what is the easiest way of solving this? Let's try to understand that now. So by dividing these two equations, we can see that tan theta is equal to 0.1 V1. So from this equation 1, we can substitute V2 as 4 by cos theta. And from this, we can substitute V1 as 10 tan theta in this equation. So we'll directly solve for theta. So V1 is 0.1 tan theta. Sorry, 10 tan theta. So 10 tan theta into sin theta plus V2, which is 4 by cos theta, is equal to 6 cos theta. So let's see what this equation gives us. So we have 10 sin square theta by cos theta plus 4 by cos theta is equal to 6 cos theta. So this is going to be a fairly easy equation to solve by using the identity that sin square theta is equal to 1 minus cos square theta. So we have 10 sin square theta plus 4 upon cos theta is 6 cos theta. So we can just cross multiply. And then we can just substitute, for example, we can substitute cos square theta as 1 minus sin square theta. So this will now directly give us the value of sin theta. 16 sin square theta will be equal to 6 minus 4 or 2. So we're getting sin square theta as 1 by 8 or sin theta as 1 by 2 root 2. And therefore we'll get cos square theta as 7 by 8 or cos theta as this. Okay. So once we get that, from that we can find out the individual values of V1 and V2 also. So first of all, we can see that V1 10 tan theta. So here it will become 10 into sin by cos. So it will become 1 by root 7. And V2 So these are the values of V1 and V2 that I am getting. Now you can always check the validity of these values which I have got by substituting in the original equations, okay, these equations. So you can always verify these results by substituting in these equations that I had earlier. That is V2 cos theta is equal to 4 and V2 sin theta is equal to 0.4 V1. So in this, if you substitute these values, so 8 root 2 by root 7 into cos theta, which I have got as root 7 by 2 root 2, will give me 4. So that's correct. Okay. And in this equation, V2, which I have got as 8 root 2 by root 7 sin theta, which is this should be equal to 0.4 V1, where V1 we have got as 10 by root 7. Yes, so this will also work out. So the equations are consistent. So my answers are correct. Okay, so this is my V1. This is my V2. And from these two, you can see that tan theta is this divided by this. So theta is tan inverse of 1 by root 7. Okay, so this is like a more complicated type of question.
Sir, sir, sir. Sir,
Yes.
sir, velocity of separation should be v2 sine theta plus v1.
No. Go back to the diagram, you'll understand. V2 is already along the center to center line, so you don't have to take sine component of V2. It's V1 which is at an angle of 90 minus theta. I explained that point already earlier.
Okay, sir, I got it.
Okay, so this is your center to center line. So V2 is already along this line, so we don't have to take any component of V2. It is V1 whose component we have to take. V1 is like this. This angle is 90 and this angle is theta. Hence, okay, now next there is a theorem related to this, which we should remember as a direct theorem, but we will do the theorem as a proof actually, because even in H.C. Verma, it is not given as a theorem in the theory part, but it is given as a question which you have to prove actually. A question in which the statement of the theorem has to be proved. So let's look at that. So if we have a collision of this type, where these are identical masses, and this one is at rest initially, then after impact, if their velocities become V1 and V2, this we have to prove that V1 and V2 are perpendicular if the collision is perfectly elastic. Okay. So we are also doing this as an example, but this will now become a general statement that identical mass in a perfectly elastic oblique collision always have final velocities perpendicular. So let us look at the proof of this. So as we go along, we'll see 2 or 3 different ways of proving this, but the simplest way of proving this is that we have mv0 is equal to mv1 plus mv2, momentum conservation. Okay, so this over here gives us that v1 plus v2's vector sum is equal to v0 because the masses are equal. And second, perfectly elastic we can interpret, instead of using coefficient of restitution, we can also interpret as kinetic energy conservation. So we have V1 square plus V2 square is equal to V0 square. So now it is pretty obvious from these two equations. Okay. So from equation 1, mod of V1 plus V2 is equal to mod of V0. And from equation 2, V0 is square root of V1 square plus V2 square. So this means that mod of V1 plus V2 is square root of V1 square plus V2 square, which means that V1 is perpendicular to V2. So this is one simple way of proving this. As I told you, we'll see another way of proving this also.
It's only for two equal masses.
Yes, exactly. They have to be identical masses. Otherwise, you can see the equations 1 and 2 will not be of that type.
If the masses are different, then it varies according to the situation.
Okay, so let's see another way of proving this through a question. Okay, so A and B have identical masses. and the collision is perfectly elastic. If A deflects by 30 degrees, find final velocities after impact. Okay, so there are two ways in which we can do this question. One is using the theorem. Which is going to be the easiest way actually. Okay, so if these two statements are there, then that means this. So if I use this theorem, this theorem will now tell me that if this was the initial line along which A was moving. Now given in the question that A's velocity is at 30 degrees to this. So I'll know that B's velocity, this angle theta, become 90 minus 30, 60 degrees. Okay. And once I know that, the rest the question becomes very easy to solve because we have to just use momentum conservation for the two variables. So was the situation earlier. Okay. So we have mv0 is equal to, given that v0's value is also known, suppose it is 10 meters per second. So mv0 is equal to mva cos 30 plus mvb cos 60. And along the y-axis or the perpendicular axis, so solving equation 1 and 2, we'll get this. Okay, so equation 2 will give us that you can also check that this implies that kinetic energy is conserved. Check that these values are giving you that. So this you can see is getting checked because
Sir,
yeah, what happened?
so what are the maximum number of particles can be involved in a collision?
Infinite.
Again, a question.
There is nothing, if you go through the JEE syllabus, there's nothing that tells you that the maximum limit is 10, 15, 20, any number of particles. Okay, now one more thing we can check over here is that whether or not the coefficient of restitution checks out to be 1. Okay, because the fact that it's perfectly elastic, kinetic energy is conserved, it should also mean that coefficient of restitution is equal to 1 or not. So for that, we have to check that, we have to understand the impulse picture a little more carefully. Okay. So if this is the situation just before impact, this is the impact itself, and this is the situation just after impact. So what we are seeing in this case is that this velocity v naught, okay, that some kind of angle with respect to the center to center line. And that is the line along which the collision impulse acts. And as a result of that, just now we saw that the fact that the first particle got deflected by 30 degrees with respect to this line means that the second particle is along this line. So if this angle is 30 degrees, it means that this angle is 60 degrees because they are perpendicular to each other. So going back to the first diagram, that shows us that the angle that V naught is making with respect to the center to center line is how much? It's 60 degrees. This angle here, it is 60 degrees. So what is the approach velocity in this case? Is V naught cos 60? Okay. So that is V naught by 2. Now in this diagram, we can see that this whole angle is 90. So what is the separation velocity? It is just V2 because V1 doesn't have a component along the center to center line. Okay. So if E is equal to 1, then what should happen? Our separation velocity should be equal to our approach velocity. So V2 should be equal to V naught by 2, and that is what we got. So this verifies that our result is also correct in terms of approach and separation velocity.
Sir,
Yes.
sir, along with the mass m2 which was equal, if there was another mass present along with it which was unequal, like it was say it was higher or lower than the mass which
Have
is
I
moved.
given a question with any other mass over here right now? Is there any other mass in this question?
No, sir, I'm just asking.
Then why are you unnecessarily complicating? No. Let's finish the case of what is the topic we are discussing right now. What is the heading on the topic? Oblique collision of two bodies. No?
Yeah.
I'm not completed that. No? Let's complete this first. I'll give you time for doubts and discussions after completion of collisions also. So in case there is anything you feel that is not covered during our discussion, we can always discuss that then.
Okay, sorry, sir.
No, it's okay. But just saying that first let's concentrate on learning everything with respect to two bodies. Then we'll move on to more than two bodies situation, right?
Yes.
So there are a couple of more things we have to learn in this first. Then we'll move on to multiple body collisions. Okay.
Yes, sir.
Okay. So now coming back to this same question, suppose the question was one step more complicated that we cannot use. Acha, before that, let's also see by another method. Suppose I don't make use of the theorem because I don't remember that theorem. Okay, so instead, I'm using the condition. Okay, sorry. Using the condition that perfectly elastic implies that E is equal to 1. So obviously the solution is going to become more lengthy because I'm not making use of some theorem from before. So I'm going to be having to solve things more manually, but you'll see we'll still get the same result. Okay, but it'll be like a little bit like ending up deriving the theorem, but in a different way. Okay, so this one is at rest. This one is moving at V0 along this direction. Now, what was the information given to us? The information given is that the masses are equal. Okay, and that A deflects by 30 degrees, apart from the fact that E is equal to 1. Okay. So if A deflects by 30 degrees, then we can also see that in the final picture, A's final velocity is in this sort of direction, where this angle is 30 degrees. Okay. Now that whole impulse picture will become important because so if this is the center to center line, impulse is acting along this line. So we can see that if this angle is theta here, then B's velocity will have to be at that kind of theta only. Whatever this angle theta is. Only thing is now I'm not using that theorem, so I don't know theta is equal to 60 degrees. Okay. So what I will do is instead of using x and y axis like this, I'll take the center to center line as my x axis. And I'll tell you why that becomes more convenient. So we will take this as our y axis and this as our x axis. Okay. So if I do that, now I can see that in the picture just before impact, with respect to our center to center line or our new x-axis, the initial velocity of this guy, it is at some unknown angle theta now. So what is our approach velocity? It is v naught cos theta. We don't know theta now. From the theorem, we know theta is 60, but here we are assuming that we don't know because we don't know that theorem, suppose. Okay. So in this diagram now, what will be the separation velocity?
VB.
But we can kind of assume that there is some component of VA also, no? Because we don't know that this is perpendicular. No? Okay. So if this angle is theta plus 30, how much is this angle here? Suppose this angle is some alpha. So alpha is 180 minus theta plus 30, right?
Yes.
So it is 150 minus theta, that is our alpha. So then according to this, what should be our separation velocity? Our separation velocity should be VB plus VA cos alpha. Right? Okay. So now I have two unknown quantities, okay, VB and VA. So first thing, E is equal to 1 means that approach velocity is equal to separation velocity. So this will tell us that V naught cos theta is equal to VB plus VA into this thing, cos of 150 minus theta, because alpha is that much. So this becomes our first equation. And the second thing is, okay, so actually we have three unknowns. We have VA, VB, and theta, three unknowns. Okay. Now the second thing we can see here, which is happening, is that for the particle A, okay, Y component of momentum is conserved. Can you tell me why this is happening? First of all, should this be correct? For A alone, should the Y component of momentum be conserved?
Yes, sir, because impulse is acting only along the line joining the centers, right?
Very good. Okay. So why this is happening? It is because the impulse acting on A is along minus I cap now. So there is no impulse along J cap. Okay. So the momentum is conserved. So now can you tell me what is the equation for momentum conservation for A along the x-axis? Oh, sorry, along the y-axis. So in this diagram, how much is A's momentum along the y-axis?
V naught sin theta.
So V naught sine theta. And in this diagram, remember, like I'm still assuming that y-axis is somewhere like this. Okay, I'm assuming that I don't know that alpha is actually equal to such that that's becoming V is along the y-axis. So in this case, how much it should be?
VA sin alpha.
VA sin alpha. Okay. And since I'm writing momentum conservation, so I should write the mass on both sides, but obviously that will cancel off. So that is giving me a second equation, that V naught sin theta is equal to VA sin alpha. And sin alpha, remember, is becoming this. It is becoming sine of 150 minus theta. So this is becoming my second equation. Okay. And three variables, so I need one more equation. So what is the other equation I can write now? for the system, there is conservation of momentum along the x-axis.
So it will be VA cos alpha is equal to
Yes. For A plus B,
VB.
right? Conservation of momentum along x-axis. Yes. Okay. So actually, you can see that by writing the first equation, I've already conserved the momentum along y-axis, because B is not having any momentum along the y-axis. No? So by conserving A's momentum along y-axis, actually I've also conserved the system's momentum along y-axis. You understood my point?
Yes.
For the y component, whether I had written A plus B or just A, it's the same thing, no? Because B is not having any momentum along the y-axis. So it's one and the same thing. But now for along the x-axis, so what will the equation become? In the initial picture, it is mv naught cos theta.
So
Okay. And in the final picture, it is becoming how much? In this diagram, how much is the momentum along the y-axis? Sorry, along the x-axis. This is the x-axis now.
VB minus VA cos.
Yes, BB minus VA cos. Okay. So you'll see that equation that we get, this third equation that we are getting, will be very easy to compare with the first equation. We can very easily eliminate that VA cos alpha term and get VB from that, because this is directly now MVB minus MVA cos alpha. No? So it's basically just this. No? So this is giving us that V naught cos theta is equal to VB minus VA into cos of that same term, 150 minus theta. So this equation is very easy to compare with the first equation and directly gives us VB. And once we directly get VB, okay, we'll be able to find theta very easily, I think. Okay.
So we can subtract 1 and 3.
Okay, so first we can add so that we get rid of that VA cos term, right? So that directly gives us VB. And once we got VB, okay, it will be a little bit more effort, but we can find out theta and VA also. Okay, so if you just add equation 1 plus 3, what we are getting? We are getting 2 V naught cos theta is equal to 2 VB. Right. So VB is actually becoming V naught cos theta. So the moment that is happening, that VB is this, that means VA cos 150 minus theta is how much? 0. Okay. So that means 150 minus theta is how much? It is 90 degrees. So that means theta is how much? 60 degrees. And once we got theta is 60 degrees, now we can substitute in one of these earlier equations and get the value of VA. Now we can substitute in the second equation to get VA. So substitute in second equation. So you'll get the value of VA. Okay. So for example, this method was not very clever here, because if we knew the theorem from before, then there was no problem. We could have directly substituted theta as 60 degrees. But now supposing the masses are not equal, supposing MA and MB are not equal, but the collision is elastic, then we know that the angle is not going to be 90 no, of VA and VB. So there's no way to initially say that, okay, theta should be 60 or 53 or what it should be. So then we have to use a method like this. Or suppose the masses are equal, but the coefficient of restitution is not 1. It is something else. So again, we have to resort to some way of solving like this, using the coefficient of restitution. So we will take so whenever coefficient of restitution is given and some information like this is given, other than the special case where E is equal to 1 and M1 is equal to M2, we will have to take the resolution of the vectors like this, that one axis, the x-axis is the center to center line, or what we call the line of impact. Now, because the impact forces are acting along that line. So we take that as one axis and perpendicular to that as the other axis, so that it becomes easy to write the approach and separation velocity. So this method too that we are using, we can use it as even a more general kind of method, even when E is not 1 or M1 is not equal to M2, or both the cases that neither M1 is equal to M2 nor E is equal to 1. Okay, so people, are you getting the values now of VA also by solving, substituting?
Yes.
We're getting now. Let's just check out. So what is second equation telling us? It is telling us that V sine 60, because theta is now 60 degrees, is equal to VA sine of 150 minus 60. Yeah, so that is telling us that VA is equal to root 3 by 2 V naught. Okay, so this is showing us that this method will also work. Okay. So the equations here are clear. Have you finished writing down?
Yes, sir.
Okay. So now, as I was telling you, that we can use this method as a more general method, even when the theorem is not applicable. So when is the theorem not applicable? When either coefficient of restitution is not 1, or the masses might not be equal, or both the things, that neither the masses are equal nor E is equal to 1. So when something like that happens, so there is no way we can apply that first method. So we'll have to use this general method. So let's see an example like that. Okay, so next example. Let's keep both the factors different, that neither the masses are equal, okay, nor the coefficient of restitution is 1. So we are solving like the most general situation. Okay. So now this one is at rest, P is at rest, and E is moving with an initial velocity V naught like this. So given that the masses are supposed in 2:3 ratio, P naught is 20 centimeters per second, and this time, suppose make it a little bit easier, coefficient of restitution is 2/3, and I make this little easier by saying that B has a velocity PB at 53 degrees with respect to V naught after impact. So we want to find magnitude of VP and VA after impact, and we also want to find the angle between the two vectors. Okay. And this time we can be pretty sure that it will not be 90 degrees, because those conditions are not satisfied. Neither the masses are equal nor the coefficient of restitution is 1. So first, just make sure you get the diagrams correct. Okay, from this initial picture, draw the picture just before impact, during impact, that is like the center to center line, the impulses acting, and then after impact. Okay, so that you can compare those two, and from that you can easily understand how to apply the two things, the conservation of momentum and the coefficient of restitution condition. Of course, conservation of momentum itself will involve two equations, because there will be two components. And because we are using the coefficient of restitution, we will not take the x-axis along V naught. Rather, we will take the x-axis along the line of impact, that is along the center to center line. So that is the general method to use. Okay. Okay, so anybody got the values of VB and VA? VA will be a little complicated, but VB will be quite simple actually. Okay, so just continue with the working. I'm just making the diagrams in the meantime. Okay, so this is so this is our center to center line. So in this question now, one thing that is easy for us is we already know the angle of this center to center line with respect to the initial velocity V naught. You'll realize why we know that, because B's final velocity will be along the impulse now, because B was at rest initially.
So,
Yeah.
so the angle between them is approximately 83.
Okay. And what about the values of VA and VB? You got?
They're finding them.
Okay. So this angle, suppose this is theta. So this theta will be how much?
53.
Yes, this theta only will be 53, because B's final velocity is along this line only, no? Whereas A's final velocity is at some random angle, let's say VA, like this. So this angle is the same theta as that one. So you can see that from this information, you can see that theta is equal to 53 degrees. Okay. So now let us do that only. We'll take this as our x-axis and this as our y-axis. So now what we'll do is, instead of taking some angle and all that, we'll take components of A along this and this. So let's say this is VAY and this component is VAX. So we can see that VA will be square root of squares of these two. So this will be easier. So what we want to do now is we want to find VB, we want to find VAX, and we want to find VAY. So we have three unknowns. So the equations that we'll use for this is conservation of momentum. Okay. So that will be giving us two equations, and coefficient of restitution being 2/3. That will give us one equation. And these will be linear equations, so they'll be quite easy to solve. And once we have found out VAX and VAY, we can express VA in vector form and VB in vector form. And we can use vector algebra to find the angle between the two vectors. Okay, so I know we have exceeded the time, but I just want you to take a couple of minutes to write down the equations. I'll explain the solving very quickly, but so you get confidence in writing the equations yourself. Okay, so now I'm writing down the equations. So you can see that in the first diagram, the approach velocity is V naught cos theta. In this diagram, the separation velocity is VB plus Vx. Okay. So the coefficient of restitution is 2/3, implies that separation velocity is equal to 2/3 of approach velocity. And theta is 53. So this equation will further reduce. Now Now this will become cos 53 is 3 by 5 into 20 centimeters per second. So 12. So this is our equation 1. Then we'll write the momentum conservation equation along x-axis. So for A plus B, momentum along the x-axis will become MA V naught cos theta is equal to MB VB minus MA VA. Okay. So masses were 2 and 3 kg. So once again, 2 into 20 into 3 by 5 is equal to 3 VB minus 2 VA. So this equation becomes 3 VB minus 2 VAX. Sorry. So 2 VAX is equal to 24. Okay, so now you can see directly solving 1 and 2 itself will give you these two things, VB and VAX. Okay, and the other equation is very simple, it's just a direct conservation. For A alone, the y component of momentum is conserved. So MA V naught sine theta should just be equal to MA VAY. So A's y component of velocity should be V naught sine theta, which is 20 into 4 by 5 or 16. So this is directly giving us this variable. Okay. Whereas solving equation 1 and 2 will give us the other two variables. So for example, here if I just add these two equations, I'll get 4 VB is equal to 12 plus 24, 36. So VB I'm getting as 9 centimeters per second. And therefore VAX I will get as, from this equation we can see just 12 minus VB by 2. So 1.5, 3 by 2 centimeters per second. Okay. So finally we can see in our coordinate frame, VB is coming out to be 9 I cap in meters per second. And VA with proper sign convention and all that is this plus 16 J cap. Okay. So now we can find the angle between them. If angle between A and B's final velocity, or between VA and VB, is alpha, then cos alpha is, it's a bit of a lengthy operation and we'll get some unusual value. And you will see that it will get a negative value, which means that alpha is an obtuse angle, which you can see in the diagram. Oh, just a minute, people. There is a correction here. There is no 2 in this equation. Okay. You can see the separation velocity. So this is wrong. There is no 2 here. I'm just making a correction. So this operation, wait, so we'll have to change the whole set of values. Okay, so let's see now. So what we'll have to do is to eliminate this, we have VB plus VAX is equal to 12. And we have 3VB minus 2VX is equal to 24. So let's divide this whole equation by 2. Okay, and add these two. So we have 3 by 2 plus 1 VB will become 12 plus 12, 24. So this will give us the correct value. 5 by 2 VB is equal to 24. And then that will mean that VX is 12 minus VB. So that is 2.4 centimeters per second. So finally, we will get VA as minus 2.4 I cap plus 16 J cap. Get VB as 9.6 I cap. Okay, people. So with that, we conclude today's session. We'll pick up from oblique collisions again in the next lecture. That's it, and thanks for attending. Wish you a nice day.
Thank you, sir.
So in the next lecture, we'll be having situations where both the bodies are moving.
That also, and like a little bit more complex situation where we have to work out the angles from geometry and all that. Like in this question, you can see directly the angle was given.
Yeah.